today I have Donal and Leon. I'm going to give just a quick introduction. Donal Skelly is our product manager for our dissolved gas analysis line. Donal has a lot of field experience with this product set. We're happy to have him with Qualitrol and looking forward to some of the technical analysis he's going to give us today. Joining Donal is Leon White, who's our Midwest sales manager for the Qualitrol and also the DGA lines. Leon's been with us for about 5 years, has some vast experience outside of that as well. Next slide for me, Donal. I do want to call out, based out of Fairport, New York, which is where our headquarters is for Qualitrol, we are going to be covering a variety of the Serveron product line. For those of you that are familiar with Qualitrol, we do have a number of manufacturing sites. So Serveron is where our DGA is primarily focused out of. So as we're talking about a couple of these different product lines, just to make sure everybody is clear on what we're talking about today. And last but not least, as far as the products itself, despite the portfolio that Qualitrol does have, today we're focused on the transformer line specific to the vault. So as you have questions about other parts of the product line, please let us know. We'll do what we can to answer, but today's presentation will primarily be focused on the transformer itself and again, specific to vault transformers. So with that said, again, if anybody has any issues, please reach out to me through the chat or the question function, but I'm going to let these fine gentlemen take it away. You guys on mute?
Okay. Can you hear me?
I can hear you now. Take it away.
Okay. So this is Leon White. Happy to be here. Hope everyone on the call finds a lot of value in what we're about to talk about. So some of the primary products that we use in vaults today are our DGA150, our ITM 509, and our QTMS. And so just a little background on the DGA150. It's a hydrogen monitor, and it can connect to a variety of different products, including the 509 and the QTMS, to provide hydrogen monitoring into the system. The 509 is an overall product, I guess, that brings a number of different inputs into it. Can have up to 16 inputs, which is great for monitoring 1 or 2 transformers in a vault. But some of our customers like to monitor 4 or 6 or more transformers in a vault, and that's where our QTMS comes in, because it's easily expandable and can monitor many transformers at the same time from all the various things that you'd like to monitor on the transformer. Okay, and so I assume, since this is a webinar on vault transformer monitoring, most people know what vault transformer is and where they're located, but typically, for those that may not be as familiar, typically these vault transformers are actually in vaults below ground. These vaults typically can be flooded with water, and so submersible products are important. Field gauges and submersible DGA monitors and other types of monitoring like the 509 and QTMS in submersible enclosures. All that's very important for most vaults. The picture on the left is actually a vault in the bottom of a large building. And so I believe that vault, normally they're not that large. That vault, I think, has 6 transformers in it, whereas the diagram on the right shows much more typically what you see is a very tight and cramped vault with the transformers inside, although most of the time the transformers are square. I've never seen a round vault transformer like the diagram shows. And so okay. Donal will take it from here.
Okay, thanks, Leon, and thanks, Matt, for the introduction at the start. The following slides relate to monitoring in general. We'll look a little bit more at our vault products, and at DGA, we'll focus quite a bit on DGA. So the first question to address when considering voltage monitoring is a pretty basic one. Why monitor at all? And especially if you have not been monitoring these transformers in the past, or if monitoring has been very basic in nature, and now what we're considering here is something a little more advanced. The question might be, why change what has worked in the past? So for most utilities, what's worked in the past might no longer be good enough. Demand on the networks to be ultra reliable and ultra safe, to be low cost to operate, and to achieve this with, in a lot of cases, reduced personnel. It means that modern technology can and will play a part in achieving these divergent objectives. Also, we need to consider the safety aspect of voltage transformers. As we'll see on some later slides, voltage transformers can and do fail. They fail in urban areas, and this can create a risk to the public. And monitoring will help to mitigate that risk by informing the user of an emerging risk. A key thing to take note of here is that monitoring won't stop a transformer from failing. What it will do is it will help inform you when there's a risk of failing, or if the transformer is showing excessive aging. And it will allow you then to take some action to prevent that failure or to manage the aging of the transformer. Okay, so monitoring can help me to manage my assets, potentially save via condition-based maintenance, and maybe even to save lives in an extreme circumstance. But what about saving money? So if we look at this from the perspective of what the cost of failure is, and considering the costs that are different at different utilities and at different levels on the electrical grid, what I'm showing here is just cost in the most general sense and applying a relative scale, as indicated by the dollar sign. So the more dollar signs, the more expensive. But it's very much a general relative scale. And actually, this list is not mine or Qualitrol's opinion. This is taken from a CGRE report. It's referenced there at the bottom. And it details the cost benefits of monitoring. It does consider all levels of the grid, so maybe not all of these apply to voltage monitoring, and we'll consider that. So what do we have? If a voltage transformer fails unexpectedly, we might expect to see a large cost to remove the old transformer and replace it with a new one. If it fails catastrophically, there can be increased removal costs, and it might not just be the transformer that has to be replaced. All of the infrastructure, ancillary equipment, cables, communications equipment, etc., can all get damaged and would require replacement. Costs can be huge if there's a catastrophic failure. If it's a routine failure, there's still labor and equipment costs, and these can be significant. Maybe you have additional routes for the power, so there's no cost of lost capacity generally with voltage transformers. Those costs are more associated with large transmission transformers or even GSUs. And there's no cost of purchased power, but there is going to be additional stress on other equipment as power is rerouted, and that will have some cost because it will result in some level of increased aging of that equipment. If it's a building or business which is a supply contract and the power goes out, there might be fines for service interruption. This is quite common in some parts of the world. While it's hard to quantify reputational damage to the business, if the power goes out at the wrong time, and I'm thinking here of like a big football match or a public event attended by the media, this can have implications, even to the extent of implications for the share price of the company, especially events that get into the media or something that happens in downtown. Cost of environmental damage can be hard to quantify, but if there's an oil spill or other environmental impact, you can be sure that the Environmental Protection Agency or some other national agency will be able to quantify that cost for you, and that can be huge. Voltage transformers have an end of life. Generally, there are two processes by which they will reach that end. One is they're managed through their life cycle and replaced immediately before the end of life. And the other alternative is that they fail unexpectedly. So how can we ensure that you can achieve the first and avoid the second? And what we're discussing and showing here today is that can be achieved through monitoring and managing the transformer through its lifetime. So as I said before, monitoring won't prevent failure, but it will allow you to manage the asset in an informed way. It won't prevent them from reaching their end of life, but it will warn you when the end of life is likely to be. In particular, for transformers, dissolved gas analysis is a very powerful tool for fault detection. It's been used by the power industry for the last 40 or 50 years. Not often deployed on vault transformers because of the difficulty of access to take out an oil sample. We have, of course, over the last number of years, and Qualitrol have, and you'll see it today, a product which is suitable for the vault application and can do dissolved gas analysis online. So Liam has spent a fair portion of his career in vaults, and he's going to talk a little bit more about the vault transformer environment.
Okay. Well, as the picture on the left there shows, typically inside a vault it's very cramped. The access is difficult. Most of the time you're going through a sidewalk or sometimes even in a manhole that's in the middle of a street. And when, as the picture on the right shows, when cables fail or transformers fail, the public generally is going to know about it well before the utility because of the smoke and or flames coming out of the sidewalk. So, of course, these are things we want to do our best to avoid. And in addition to the public safety, we also want to ensure the safety of our employees that are working down in those vaults. And having remote indication of the health of the transformers is very important. I've actually talked to some smaller utilities that have vaults that have said, well, they've never had a vault transformer failure. And so when I ask them how old is their fleet and, you know, how long they expect these transformers to really last, they say, well, our fleet is 20 to 30 years old and we don't know how long they're going to last. And so the generation of employees that installed those transformers are probably about to retire or have already retired. And now the people that are left to take on the challenge of working with these 30-year-old transformers, it would be very good to have a good idea of what the real health of these transformers are and have online tools to be able to tell people that it's safe to go into the vault before they do actually go into a vault. If I can get the slide to advance here. Donald, I might need your help on that. There we go. And so now I'm going to talk about physically, you know, it's great to say, oh, we've got all this good information coming back from vault. How do we get that information? And so you can easily order monitoring equipment on new transformers, but of course, any amount of new transformers that you install are simply an extremely small percentage of the total that you have installed. And so the majority of the work to install monitoring on vault transformers is going to involve retrofits. And so we've got some pictures here of some actual installations. And at the top, in the top picture, we have one of our DGA150s, so that is monitoring hydrogen in real time. Typically, vault transformers have two oil compartments, one for the switching compartment or the primary switch, and the other one is the main tank. Due to the separate oil compartments, you need to monitor the hydrogen in each compartment individually. And therefore, the diagram on the right shows that you can install DGA150s on each of the drain valves for each tank. And then the picture at the top left shows a DGA150 installed on an actual transformer. If you're interested in monitoring your temperature or your oil level, which are very important things, the temperature and oil level gauges can be easily removed and replaced with gauges that have analog outputs that can be fed to like a 509 or a QTMS or other equipment. The gauges, typically there's normally 2 or 4 screws that can be removed to remove the existing gauge. Temperature gauges, a lot of times, are direct mount gauges that you just unscrew the gauge out of the well, and then you can install the replacement gauge right back into the well. We have Qualitrol, typically in North America. Most gauges on existing transformers, whether they have a Qualitrol name on them or not, were actually manufactured by Qualitrol. So we have an extensive capability to be able to provide replacements for those gauges. Standardization over the years has been very difficult, and so if you look at 5 different transformers, chances are the gauges on those transformers will be different for at least 3 of the 5. We can also monitor the pressure in the tank. So typically you like to keep positive pressure, nitrogen pressure typically on these transformers, so that they don't, in cold weather, the oil level will go low and can draw a vacuum if there's not positive pressure. And so pressure is another thing we can easily monitor. We can just put if it's got an existing pressure gauge, you can put that pressure gauge on a T and install a pressure transducer coming back into like a 509 or a QTMS. And so the picture on the right side of the box shows an existing an installation of a pressure gauge with a pressure transducer. Okay. So, yeah, Donald, looks like you need to advance it for me.
Oh, okay, Liam, sure.
There we go. And so for a little bit closer pictures of actual installations, typically on vault transformers, your liquid level gauge is a 3-inch gauge. And so before, if you notice at about the 8 o'clock or 8:30 position and 2:30 position, there are 2 screws on that gauge. You simply remove those 2 screws. You pull the existing liquid level gauge out. Despite what you might think, typically there's pulling the liquid level gauge off, there's no oil that comes out. It's simply a magnetic gauge that all the oil stays in the transformer. You don't have to lower the oil to replace that gauge, and you just pull the face of that gauge, or the case, off is what we call it, and then you put the new gauge on with the analog output. For temperature gauges, again, those are typically installed in wells. So again, when you remove a temperature gauge, no oil comes out of the transformer, and so you don't need to lower the oil level. You simply remove the gauge out of the well, you install a new direct mount gauge into the well, and the new gauge has an analog output so that we can see the temperature remotely for the temperature gauges on the switching compartment and the main tank. You can go to the next slide, please. And so we do have, for extremely corrosive environments, typically our standard sealed gauges work very well in vaults, but in areas that have extreme corrosion, possibly in saltwater areas, or if you're near some type of refinery or chemical plant, we do have a full line of stainless steel products, from pressure relief devices, pressure bleeders, sudden pressure relays, and a full line of stainless gauges. So that's called our Qualitrol XTREME product line. The next slide, please. So now Donal will talk about specifics on our DGA monitoring.
Okay, thanks, Leon. Okay, so we have a few slides now focused on DGA, and the reason that the focus is on DGA is because it is one of the modern advanced monitors for vault monitoring, and it provides a lot of information that before now would have been unavailable or extremely difficult to get as an offline technique. So I expect that everybody on the webinar has some knowledge of dissolved gas analysis, but in summary, DGA is a preventative maintenance monitoring technique. Whereby the concentration of gases dissolved in transformer oil is quantified and related to the health of the transformer itself. Very well-established, well-known technique for power transformers, for GSUs, but the same principles apply regardless of what level of the grid the transformer is in. The relative concentrations of gas may be slightly different, but the mechanism by which those gases are created is the same. So yeah, where does the gas come from? Press board, insulation paper, and the oil itself are very stable materials. But if they're stressed, they will break down, and they'll produce breakdown byproducts. In the transformer, this stress is associated with heat or electrical discharges, and results in cellulose producing, among other things, carbon monoxide, carbon dioxide, and the oil producing a wide range of breakdown products, including a range of gases that will then dissolve into the oil. We'll look at these gases on the next slide, but the thing to note here is that the gases are produced when the transformer is under stress, and this stressed condition is or can be closely associated with fault conditions within the transformer, although even a healthy transformer will produce some gases, just very, very slowly. So DGA is a process whereby we measure gases that are produced under stress condition in the transformer. If we know what to look for, we can relate the concentration of gases to a particular fault type. And we'll look a little more closely at that in the next slide. So DGA is the measurement of 8 gases found dissolved in transformers. They're called the 8 key fault gases, and they have been established by various industry bodies and researchers, with this technique emerging in the 1970s and evolving ever since then. Ideally, in a vault application, we would monitor all 8 gases. However, 8 gas DGA tends to be prohibitively expensive, and it tends to require reasonably easy access to the transformer and the monitor itself. So for our DGA product, we monitor hydrogen, and I've highlighted hydrogen here, and the question is, why hydrogen? And the answer to that is that hydrogen is formed in abundance under almost all fault conditions. So if you look at this chart on the right, it basically on the y-axis it's showing the various different gases that are produced when oil breaks down, and on the x-axis it's showing a rough temperature scale. And we can see that the first gases that are produced as temperature rises, and that can be associated with heat stress, is hydrogen and methane. As the temperature continues to rise, the concentration of the gas that are produced changes, but if you notice for hydrogen, it's always increasing. So hydrogen is considered to be a universal fault gas, and it is produced when there are partial discharges, when there are hot spots in the transformer, as a result of arcing. The production of the other fault gases is dependent on the temperature profile within the transformer, but hydrogen is always produced, universal fault gas. Again, why hydrogen? So 2 reasons shown here. If we continuously monitor hydrogen, we can see not just the concentration right now, but the changing concentration with time, something that you can't see with offline testing. And therefore, we know the rate of change of hydrogen, and the rate of change can be related to accelerated changing conditions within the transformer. If you have a fault and it's getting worse really, really slowly, you may not take any action. If it's getting worse really, really quickly, as indicated by the rate of change of the gas concentration, that's a different story. Looking at the concentration itself, so the ppm concentration provides some quantification of the severity of the fault for the simple reason that the more gas present is likely to equal to a more significant fault. So concentration equates to seriousness of the fault, and rate of change equates to the trend. But it's important to note that both values are related to both conditions, and they're never considered in isolation. Both are important, and it's for this reason that there's significant value to online monitoring. It gives you a day-to-day picture of the condition based on these 2 important parameters. This is a slide that Leon has put together, and he's going to talk you through the subtleties of what we can see here.
Okay, so as Donald's prior slide showed, at lower temperatures, hydrogen starts getting produced, and as the temperature increases, hydrogen is created in the oil at a faster and faster rate. So the diagram at the top of the slide shows on a percentage basis based on temperature. So you've got temperature on the x-axis and percent on the y-axis. On a percentage basis, at very low temperatures, say in the partial disk or PD region, you produce almost 100% hydrogen. And typically PD is characterized in DGA by a lot of hydrogen followed by methane. And so as the temperature increases, on a percentage basis, the amount of hydrogen that you see in the middle range, where the methane, ethane, and ethylene are being created, typically you see hydrogen, the amount of hydrogen in the oil on a percentage basis is lower than your methane, ethane, and ethylene. And so it's not that Donald's slide, prior slide was incorrect, that in the mid-range we are producing a lot of hydrogen, but that hydrogen is actually being consumed to create the methane, ethane, and ethylene. So a lot of times people will say, well, I look at my DGA report and I've got methane, ethane, and ethylene, but I don't have any hydrogen. And part of that is because the hydrogen is being consumed to create the methane, ethane, and ethylene. The other part is that hydrogen is the smallest molecule and will leak out of the transformer faster than any of the other gases. And so typically if hydrogen was created 6 months ago and there was a significant amount of free hydrogen in the transformer, you might take a DGA today and find out that today there's no free hydrogen in the transformer, but you do see the methane, ethane, or ethylene in the oil. And it's not that the hydrogen wasn't created, because if the hydrogen wasn't created up front, you wouldn't have the methane, ethane, and ethylene. And so as you get hotter and hotter, once you start creating acetylene, all the other gases are dropping off, the methane, ethane, and ethylene, and you're left with acetylene, which is C2H2. You only have one hydrogen molecule there, so when you're producing acetylene, you also produce a lot of hydrogen. So the graph at the bottom of the screen shows that at lower temperatures, such as in the PD range, you see a significant increase in hydrogen. And as you get into the middle range, your hydrogen is still increasing. The amount that you're generating isn't going down, the free hydrogen in the oil. It's still increasing, it's just at a lower rate than in the PD range. And then once you get up to acetylene, you produce a significant amount of hydrogen again. So the takeaway from this slide is that if you're seeing a significant increase in hydrogen in a short period of time, typically it's going to be because you have partial discharge or arcing happening in your transformer, and it's going to alert you that you need to go take an oil sample to do a full analysis of what's going on in that transformer. Because if there is arcing going on, especially in the main tank, in the switching compartment, it's normal to have some amounts of acetylene. When the primary switch is activated, it's typically activated while the transformer is energized, so that that will create some amount of acetylene. But if either compartment is generating significant amounts of hydrogen, it's going to alert you that something's not right, and you need to take a look at that. Okay, so if we can advance the slide, Donald.
Okay.
So we'll turn it over to Donald.
Yeah, let me just jump in. We had a quick question that I think is a great opportunity to answer it here. So if you're only seeing an increase in the hydrogen, are you then attributing that to an internal fault?
Okay, so the increase in hydrogen is due to some amount of something getting very hot inside the transformer, breaking down the oil, which is a hydrocarbon molecule, and that releases free hydrogen and carbon that ends up many times turning into carbon monoxide, carbon dioxide, or your methane, ethane, or ethylene. And so significant amounts of hydrogen indicate, in DGA terms, a fault is defined as basically any event that's going to create gas in your transformer. And so it's not necessarily a hard fault like we typically talk about, where there's a fault on a transmission line or something. So inside a DGA-related fault refers to something that is overheating in the transformer that is generating these gases. And so significant amounts of hydrogen indicate that something's going on, and it's going to alert you that by taking an oil sample and looking at the other gases, it'll give you a lot more information about what type of fault is happening in the transformer. But transformers generally, under normal conditions, should not be creating significant amounts of hydrogen. Hydrogen does indicate that there's some problem in the transformer.
Great, thanks. Donald, we'll turn it back over to you, but I wanted to address that why it was right on the slide there.
Thanks, Matt.
Okay, Leon, great insight there. Okay, so we've looked at why hydrogen. Let's just very quickly look at a few other questions. So how much hydrogen? This is quantified by the standard shown here. So C57104 details 4 separate conditions that can be designated by the concentration of hydrogen. So together with defining the concentration limits or ranges for hydrogen, IEEE also provides some guidance on actions to take if you reach or exceed those limits. And these are general guidelines. You know, local knowledge might impact some of these levels at a utility level or at a particular transformer design level. But these are good guidelines. We're looking at concentrations between something less than 100 ppm and, you know, approximately 2000 ppm. That's the type of ranges that we're looking at. And within those ranges, it will help you to drive some decision making. So then we've talked about it already, but what about the rate of change? And this is the second parameter that you will get from these online monitors. Again, we can go back to international standards for rules, and we can see that IEC provides some intelligent guidelines. So IEC provides 3 criteria. One is that the typical rate of hydrogen gas increase in the transformer should be less than 5 ppm per day. An increase in gas concentration of more than 10%, so percentage rather than ppm, per month above typical concentrations is generally considered a prerequisite for pronouncing an active fault. So if you see a 10% increase of concentration relative to what you had, then it's likely to be because of an active fault. And significantly higher rates of gas increases, such as 50% per week, are generally considered serious, especially if they exceed alarm concentration values. And we've just seen alarm concentration values. So the guidelines are quite broad, but nonetheless, they provide you with a quick and easy mechanism to make decisions on what action you might take.
And Donald, if you go back to the previous slide, I want to make a comment. Prior one.
Oh,
there we go. So for those that have actually read IEEE standard C57.104, it is interesting to note that these guidelines were published, and it talks about in the guide that these are for large power transformers, which of course typical network transformers are not going to be considered large power transformers. But I have talked to Dr. Michel Duval, one of the foremost world leaders on DGA analysis, and his comment when I asked him about DGA and small transformers versus large transformers is that in general, these guidelines apply to any size of oil-filled transformers. So from a statistical standpoint, he has not found that small transformers generate significantly more gas than large transformers on a parts per million basis. That if you have 50 ppm of hydrogen in a small transformer, that is going to be pretty much just as significant as 50 ppm of hydrogen in a small transformer. But due to the smaller volume of oil, smaller transformers can have significantly more faster rates of change of hydrogen just due to the smaller volume of oil that the hydrogen's dissolved in. And so most of the time you never like to see hydrogen in your transformer, but I have found through experience that smaller transformers can have significantly larger amounts of hydrogen than what you typically find in large power transformers. But according to Dr. Duval, overall, there's not a significant difference. If you have high levels of hydrogen in a small transformer, it is something that you definitely want to be concerned about, just like you would be if you had high levels in a larger transformer. Okay?
Yeah, Leon, and I think that sort of illustrates as well the value to looking at rate of change as a percent. So if we look at the next slide, two of these criteria do describe changing on the basis of percent, and therefore large or small transformer, the phenomenon for creating the gas is the same, but as you say, there's a much smaller volume, and therefore you may see a faster rate of change, but it's percentage based, and that adds a little bit of flexibility in the interpretation. Also, I think it's important to say that we're talking here generally about network transformers, about utility transformers. If we are talking, for example, when we say small transformers, about a pad mount transformer for a wind turbine, those values may differ. They may differ considerably, but what we're talking about here is network transformers, and of course, volt transformers are by far the most common example of that. So we looked at why hydrogen, how much hydrogen, what rate of change of hydrogen. Just a couple of slides now, and we're not far away from the end here. Just a couple of slides on the DGA monitor and the technology in the Qualitrol DGA monitor. So Serveron/Qualitrol have a range of different DGA monitors from single gas up to 8 or 9 gas. What we're looking at here is single gas monitors, and specifically what we're looking at is the monitor that we call DGA150. This is our solution for the volt application. The distinctive feature of the DGA150 is that it's IP68, so it's fully submersible. And that's a feature that, from speaking to people within the industry, can affect up to 50% of all transformers in certain utilities. So there will be 50% of transformers that will be at least at some risk of flooding at some point in time. And DGA gives you submersible measurement of hydrogen. In addition, DGA150 can operate in either the oil phase or in the headspace of the transformer. So it has flexibility to be configured to measure gas in oil or gas in headspace. The monitor itself, and it's shown here beside its sister products, which are not IP68 but use similar technology. The DGA150 comes with a 1.5-inch NTP union fitting. You cannot really see it on the diagram here, but it's the same NTP fitting at 1.5 inch as shown here for the DGA250. And you can go, with adapters, you can go to different size connection points. It's not mandated that it can only be connected to a 1.5-inch output on the transformer. Incidentally, the DGA250 and 400 are for pad-mounted transformers. The same sensor, the same performance, but they both have an integrated rapid pressurized relay. And the difference between those two products is just the connection point. One of them is a 2.5-inch NPT union fitting, and the other is a flange mount. I'm going to quickly go over this because I know it may not be of a lot of interest to most people on the call, but the secret behind the DGA150's performance is the sensor. And the sensor is unique, and it's ideal for two reasons. First of all, it can be directly immersed in the oil, and it can measure gas in the oil itself. So this is a real benefit, because traditionally, measurement of gas in oil, either in the lab or in the field, has always involved extraction of the gas from the oil prior to measurement. And most of the other Qualitrol products do require gas extraction prior to measurement. Typically, this is achieved using a membrane or a headspace extraction system. But generally, it's not a bad thing. It introduces complexity to the system. And in fact, for these type of single gas applications, membranes can introduce some variability into the analysis, and they can potentially be a weak point in the physical structure of the monitor. And the second thing is, and this is, I suppose, the science behind this, so a thin film palladium nickel alloy based lattice. So that's what we're seeing here on the left hand side. Absorbs and desorbs hydrogen as it comes in contact with the sensor. And essentially, I mean, without getting into the subtle details of it, the hydrogen molecule can fit into this palladium lattice. In actual fact, the hydrogen, the two atoms dissociate for themselves. They fit into this lattice, and in the process of doing that, they change the electrical properties of the lattice. Those changing electrical properties are related to the concentration of hydrogen, and as the concentration goes up or the concentration goes down, you will get a change in electrical signal from the sensor itself. Since it's solid-state device, it's immersed in the oil or indeed left in the headspace. And since the sensor does not degrade as part of this measurement process, so the sensor makes the measurement without being consumed by the measurement, which is a common feature of sensor technologies. This type of sensor doesn't degrade over time, so really well suited to difficult to reach applications where you want to install it and forget about it. How does the gas get to the sensor? So in common with most of the single gas applications out there, it's via convection. And that's the same way that the gas gets to the sampling point if you're taking a sample to send to the lab, thermal convection, right? So the oil in the transformer is in constant motion, assuming that the transformer is under load. There's usually no forced oil circulation in a bulk transformer, so it's convection that's driving this oil. The process of circulation may be slow. It may take hours for the oil, for gas produced to get to the sampling point. But for a transformer faults in general, they take weeks or months or years to develop. So taking hours to detect the production of gas is still extremely rapid. And in any case, the alternative, taking the sample to the laboratory, is still at the mercy of that oil needing to circulate, and you only get a snapshot from the lab. And of course, if you use the headspace application of this sensor, so that gas naturally will distribute itself between the oil and the gas phase or the headspace phase of the transformer. So I'll hand back to Leon now, who will take you through the last few slides of the presentation.
Thank you, Donald. In reality, when we bring that hydrogen data into a product like the 509 or a QTMS, these monitoring products can provide a wealth of information on the trending and maximum and mins available in our software in these products. And so there's a list there. The last reading, of course, today's average, minimum, maximum. You can do, everything's configurable, and the configurability is very consistent between our products and being able to provide these things. One of the most valuable things, of course, is a history graph showing what the history of the hydrogen has been, and knowing what the history is helps you understand a lot better what the rate of change is. Rate of change is another thing that we can calculate in these products, and as a matter of fact, for those that are involved with IEEE C57.104, IEEE is soon to release an updated standard that will include rate of change standards as well. But as Donald mentioned, IEC already has some guidelines on rate of change. And so if you can advance the slide, Donald. Okay, so key takeaways. Again, you can improve the reliability and safety of the folks of your vault transformers, and of course, safety is a major concern. Always has been, but gets definitely a lot more emphasis today than it used to. And so being able to know that you're entering a vault that is safe is definitely preferred to entering a vault where you have no idea what the health of that transformer is. We have a number of products, primarily what we've seen customers use in vaults are ITM 509 and QTMS. They're both excellent platforms to monitor a wide range of things that you like to monitor on your transformers. And as Donald has gone to some extent on, the DGA150 is an exceptional device for monitoring the hydrogen in these transformers. It's easy to install and can bring you a wealth of information about the real-time health of your transformer. As utilities have recognized for years, DGA is the premier technology to understand what the true health of a transformer is. So next slide. Okay, I guess we're ready for some questions. Matt, do you have any questions from our folks?
We do have a couple, so I just want to take a second. I want to thank both Leon and Donald for their excellent presentation. We're going to open it up to Q&A now, so we'll give folks a couple of minutes. We do have a couple questions in there. I do want to just reiterate to everyone on the call, I want to thank them for joining us. And again, we've recorded this presentation. We're going to send out a copy of the presentation as well as the slides to everybody. So hopefully we'll get that out to you tomorrow morning. If you have any questions we weren't able to address or anything else or need more information, just go ahead and reply to that email. It's going to come from info@qualitrolcorp.com. You can use that really for anything that comes right into our customer service team. So the first question, I'll kind of answer a bit, and then Leon, I want to kind of get your take. It was about the stainless option. There was some confusion about that line, and I think they were talking about the XTREME. which is part of, really stainless is an option on any of the products that we happen to sell. So anybody who's confused about what that means or what the XTREME is there, that's kind of our branded term for anything that comes in a stainless option. But as with any of our products, we can customize those as needed, and as Leon kind of alluded to, high corrosive areas, anything submersible, that is a great option. And then Leon, I kind of want to open up to you. The question was about the benefit of having that stainless. So can you speak a little bit just about how that enhances the product life?
Sure. So we do have some customers that instead of installing standard type gauges and DGA 150s in vaults, they do opt for our stainless option. The benefit of stainless is just like the power transformers in very corrosive environments. The transformers rust. There's cathodic protection that's installed to reduce the effects of the environment. But some environments are just simply too harsh for standard type equipment. And so there are times when it's absolutely, it's just beneficial to have stainless products available. And so, as Matt mentioned, we do have the stainless DGA 150. We've got stainless gauges, a wide range of stainless products in our XTREME product line that will allow you to install these monitoring devices and have confidence that they're not going to degrade like a standard product might in a very harsh environment. Okay.
Thank you for that. So this question came in. I'll open it up to either of you guys. But as far as hydrogen monitoring in mineral oil, silicone, FR3, any differences in how we engage those, or anything you want to add about those different mediums?
So Donald, do you want to take that, or would you like me to?
Yeah, sorry, Leon, I was speaking with mute on. In the context of this particular monitor, the DGA 150 is suited to mineral and vegetable oil. There are, of course, silicone oils and other oils. The monitor will measure the dissolved gas in any type of oil, but it is configured leaving the factory for either mineral or vegetable oil. So we are looking primarily at applications where the oil type is a mineral or vegetable oil. For those other oil types, a sample to the laboratory is the only available technology now for fully accurate DGA, although our monitors will measure the gases.
Right, and I think it's important to note that I do have a customer that has a significant amount of DGA 150s installed on silicone transformers as well. And they understand that the accuracy might not be as good as a lab that's calibrated for silicone oil, but typically with hydrogen, as with any of the gases, it's your rate of change that you're interested in. And if there's significant amounts of hydrogen being produced, the DGA 150 will provide that information and allow the utility to act on that.
Yeah, agreed. It is still accurate, and as we've seen and we commented before, the rate of change is often related to percentage rather than some absolute concentration. So you will still get that in any oil type with the DGA 150.
The next question we got, I'm going to kind of paraphrase because I know we get this from different customers on a variety of webinars. So just to kind of, to not make it as centric to their account, for customers who are looking to start out, they're not, Leon, you mentioned this about, the fleet's old, where do we start, what are we doing? So from your experience with your customers, what is kind of the starting point to monitor? And kind of give us maybe a couple examples of how they've started and how it's worked, I guess.
Okay, so that's a great question because you got to start somewhere, right?
Right.
Well, one of the biggest challenges of installing a monitoring system on your vault transformer is getting that data back to somebody that can act on the data. So vaults are typically underground in sidewalks or in streets, and so it's not easy to put up an antenna or something like that. Although I do have some customers that use cell modems to communicate the data back using an antenna that is up near the grate, and I'm sure based on exactly where those are located, some sites are going to get better coverage than others. The majority of my customers are using either power line carrier, so the cables going into the vault actually provide the communication path to get data back to their typically their distribution dispatch system. The other option, which is from a communication standpoint probably preferred, is to pull fiber in between each vault and run all the data over fiber communications. And so the nice thing about having communications in the vault is once you've got that communications there, it really opens up the utility's eyes as to how the network is actually performing. They can get data from their network protectors, which is usually the first thing that they do. And then once they have the communications in there, typically for the network protectors, then they can tag the online monitoring from the transformers onto that communication path and be able to monitor the entire vault. Something else I didn't mention earlier is there are a number of items besides just the transformers that people are interested in monitoring, like ambient temperature in the vault and water levels. So, you know, sump pumps, or is the sump pump working? All those sorts of things. Those things can also be brought in through the monitoring system. But again, to get things started, each utility has to decide how best they can communicate that data back. And so really the communication infrastructure is the first thing that needs to be investigated and decided on before you actually start monitoring the devices inside the network vaults. Okay.
All right. So we've got about 30 seconds left. Again, I want to thank everybody who joined us today. Invite them if there's any other questions that they didn't submit during the webinar, email us info@qualitrolcorp.com, or just reply to the email that you get with the recording and everything. So with just those 30 seconds left, the last question, I guess, specific to vaults, Leon, what's more cramped, a vault space or the inside of a NASCAR?
That's a great question. It depends on the vault and it depends on the NASCAR. So Matt's referring to my recent Father's Day gift of getting to drive a NASCAR. So it was a very exciting weekend last weekend. So appreciate that, being brought to everyone's attention, Matt. You're a great guy.
I do what I can, sir. So I want to thank everybody for joining. I want to thank Leon and Donald for presenting. I said in the beginning of the webinar, we probably had too much fun putting this one together. A lot of good jokes, unfortunately, at Leon and Donald's expense. So we should probably do like behind the scenes on these webinars because people would get a real kick out of it. But again, thanks to everybody for joining. We look forward to working with all of you guys in the future. And again, if you have any questions, please let us know. But thanks again for joining. Have a great day.
Thank you, Matt.
Thanks, Matt.